All right, so for today's lab, should we mine this ore? We see that we have this sample of ore, and we know that it is a naturally occurring material from which metals and other materials could be extracted from for profit. Now, today we'll be looking specifically at copper, and if our ore, our sample ore, is going to be composed of anywhere between 0.2 to 1% copper, then investing in the leaching process would be profitable in the long run. So how do we go about determining whether or not we should mine this ore? Well, by knowing these concepts listed on the board, we'll be able to then construct a series of experiments that will help us derive at those answers. Now, the first part of this experiment is going to deal with our knowledge of the fact that compounds are going to absorb specific wavelengths based on their identity. And conveniently, when we deal with transitional metals, those absorb wavelengths that are within the UV or visible light range. So if we have a solution with a transitional metal that appears to look green, it would tell us that due to the complementary color, it has to absorb wavelengths within the red wavelength range. So if we look at an example of that, we see that we have a copper 2 nitrate solution, and this solution appears to look blue, meaning that it would have to absorb wavelengths of right around 650 nanometers when the copper is dissolved in this solution. So now that we took a sample of our ore, I took 1 gram of ore and crushed it up real fine, and crushed it up to provide it with more surface area to react with our different reagents so that we would want to test out to see if they're going to be a good option for our leaching process. So our first one, we're going to be reacting the ore with 6 molar hydrochloric acid, 50 milliliters of this hydrochloric acid. And we see that once it reacted, we ended up with a different colored solution. And we're going to do the same with our next 3 reagents. Our next one is 6 molar nitric acid, 50 milliliters of that. And we're going to want to stir it to, again, allow it to react a little more. And then 50 milliliters of 6 molar acetic acid. And do the same by mixing it. And our last one, we'll be pouring 6 molar, 50 milliliters of ammonia into our sample of our ore. And once we mix that, we get another solution that appears to have a specific color. So we allow it to react and sit there, and we see that there is no any additional changes happening. But again, we want to make sure to record our observations. So when we are going to record the information, we see that when it reacted with the hydrochloric acid, we got a green solution, right? Green solution. And when it reacted our ore with our nitric acid, we got nothing, right? No real reaction occurring. The solution didn't change color. And same thing when we reacted it with our acetic acid. But when we reacted it with our ammonia, we ended up with a blue solution. So from the last part of the experiment, we saw that we got a green solution when we mixed hydrochloric acid with our sample of ore. And we also had a blue solution when we mixed our ore with ammonia. So since the ammonia reagent actually made a blue solution, it would indicate to us that it would absorb the same wavelength as our known solution of copper 2 nitrate. So we can use our copper 2 nitrates to make different dilutions of this solution, of this known concentration, to then construct a standard curve, and then take our unknown concentration from our sample of ore and then put it against that standard curve to see what kind of information it will tell us about its concentration. So to begin this, we're going to want to make a dilution in which we get a 0.02 molar solution of our copper 2 nitrate. In order for us to determine how much of the copper 2 nitrate and how much of DI water we will need to mix to get that concentration, we will use this equation to do so. So if we take our original 0.1 molar solution, and then we will solve for x, and we know that we want to end up with a 0.02 molar concentration with a 10 milliliter solution. And when you solve for x, you see that you will need to mix 2 milliliters of our copper 2 nitrate, and then the rest, which will be 8 milliliters of DI water, to get that concentration. And then we will do the same with every single other dilution to, again, be able to construct that standard curve. So we'll take our first beaker, label it, and we're going to get 2 milliliters. We're going to take it up with a pipette and insert it into a cuvette, for which we could then use when we are running it through the colorimeter. So once you've finished running all of the cuvettes through the colorimeter, what you could have done is either take screenshots as you were doing so, or what you could have done is write down the values that you obtained from running those cuvettes through the colorimeter. But at the end of the day, all you need to do is either go to Excel, or again with the screenshots, you need to create this graph that demonstrates the standard curve. So once you can plot all of the different absorbances, and then you get to your unknown sample, and then you take the absorbance that you received through putting it through the colorimeter, and then you can see and plot it against that standard curve that you've created to then determine the concentration of your unknown sample. And from the actual numbers that we received through the experiment, we can then determine that the concentration of our unknown solution would be that of roughly 0.05 concentration for our copper in solution.